Hello, welcome to the screencast video number 1 in nuclear, metalloorganic and bioinorganic chemistry. So, if you have a copy of your syllabus, you'll know that this is what the course content for nuclear, metalloorganic and bioinorganic chemistry looks like. I do realize as I go into this video that we haven't had the chance to discuss the syllabus at the beginning of this semester, but what I'll do right now is I'll just tell you that of the 5 units in this course, I'll be handling units 1, 4 and 5, so 3 units in total. And as you can see here, unit 1 is on organometallic chemistry and units 4 and 5 are on nuclear chemistry. So I thought we would begin this course with nuclear chemistry. We'll finish this first and then we'll go on to organometallic chemistry. And the reason I chose this path for finishing the syllabus for this course in this way is because for 2 classes, this class and next class, I'm not going to be with you people, so I'm going to be giving you 2 or 3 videos. So I thought when I'm not there in the class, instead of talking to you about organometallic chemistry via videos, it would make sense and it would be easier to talk to you about nuclear chemistry because the basics of nuclear chemistry are rather easy to comprehend in comparison to the basics of organometallic chemistry. So this is my train of thought. I do not know how right or wrong that is, but we'll see how it goes. Right, so I'm going to call this video an introduction to nuclear chemistry, but before that, like I said, I'm going to give you 3 videos over the next 2 classes, this class and the next class, and I've kept these videos rather short and simple. Each runs for about the duration of 10 minutes, so you'll be basically watching these videos, and at the end of the video there's going to be a quiz. You'll be given the printed content and you'll have to answer the questions in the quiz, and there's going to be a key, so you're going to assess yourself. This is going to be a self-assessment thing, and just to check how much of what I talk about in these videos has been internalized by you. So that's my basic plan for the 2 classes, this class and the next class. So back to this video, I'm going to call this introduction to nuclear chemistry, and these are the basic things we'll be covering in this video number 1. So we'll define what's a nuclear reaction, which I'm sure all of you already know. Then we'll go on to the very basics of the atom, which again is a recap. And the third thing, the thing of significance from the point of view of units 4 and 5, where we will be working out some problems, is the units of radioactivity. So we will be talking about this part in a little detail. So yeah, moving on to the definition of nuclear chemistry. How does one actually define nuclear chemistry? So we define nuclear chemistry as the study of the structure of atomic nuclei and the changes that nucleus undergoes. So first you study the structure of the nucleus that you're interested in, and once you've had a grasp on the structure of that nucleus, you think about what the changes that are going to happen in the nucleus as a function of, let's say, the bombardment of a particle upon that nucleus. So with that in mind, atomic nuclei here, the 2 operative words here, atom and nucleus. So with that in mind, the structure of atom that we know today is as shown here. You have a central positively charged nucleus, which contains protons and neutrons. Protons are positively charged, neutrons are neutral. They are also massless. So this conglomerate of protons and neutrons together is called the nucleus, and around this nucleus you have electrons that are revolving around in imaginary orbitals, and electrons, as you all know, are negatively charged. The other thing, this unit together, protons and neutrons, this unit together is called the nucleons, right? So this is the structure of the atom as we know it today, but you also know that the structure of the atom, or for that matter any discovery in science, does not happen overnight. So we have this structure because of the intellectual efforts of many different scientists over a long period of time, over centuries actually. So the very first person who gave us the structure of atom, or talked about the structure of atom under the rubrics of atomism, was Lucretius. Lucretius was a Greek philosopher who wrote a treatise called The Nature of Things. So what he essentially said was, take a piece of paper, tear it into half, then take one of the halves, tear it into 2 more halves, and keep on going this way until you can tear the piece of paper no longer. So what you end up with, the smallest piece of paper in your hand which you can no longer tear, is the atom. So according to loquacious, the A here in the atom is a negation, and the tome, the TOM, tome, is something that's divisible. So atome, that would mean something that's not divisible, adivisible. So this was Lucretius' concept of the atom, and moving forth, we are jumping several centuries ahead, and now we land on Thomson's plum pudding model. So J.J. Thomson, what he essentially said was the atom looks like a sea of positive charges into which these negatively charged electrons are embedded. So if you would rather think of this plum pudding model in the form of a watermelon model, this red fleshy part over here, this is your sea of positive charges, and this dark brown or the black seeds that we spit out, these are the negatively charged electrons. Now you and I also, we know today that this also is not quite right. This model of Thomson is also not quite right, and the correct model of atom as we know it today was given to us much due to the efforts of Rutherford and his team, where they did the gold foil experiment. So what they did was they took a gold foil, bombarded the gold foil with alpha particles, which are positively charged helium rays. So you have the gold foil, positively charged alpha particles are bombarded upon the gold foil, and they observed, Rutherford and his team observed, that most of this helium rays, they pass right through the gold foil, but in the central core, the alpha particles that impinge upon the gold foil, those are deflected back. So the only inference that we can draw from this observation is that something that's positively charged that hits a core and then bounces back, that would mean the core and the thing here is also positively charged. So that gave us the idea that the central core of the atom should be positively charged. Rather, the central core should be the nucleus, and not quite the model of Thomson, where he said you have a sea of positive charges and then in it you have your electrons embedded. So this is where we basically stand at now. So very quickly, a recap of what we know about the nucleus and the electrons. The nucleus constitutes about 99.9% of the mass of the atom, and interestingly it is only about 1 by 10,000 the size of the atom. So like you already know, and like we just discussed, the nucleus is positively charged because of the protons that are held there, and the electrons, like we all know, are negatively charged. So going forth with the concept of something exists rather than nothing, we know that the nucleus exists because of the strong nuclear forces. It is these forces that holds the nucleus together, and the electrons, they revolve around the nucleus in those so-called imaginary orbitals because of these weak electrostatic forces. And we also know that there's of course other concepts to talk about the electrons revolving around the nucleus, but this lecture we would not be going into that. Right. So this is the symbol of an element, carbon 614. 6 here is the atomic number, 14 here is the mass number, and if you want to find out the number of neutrons in any element, what you do is you just subtract the atomic number from the mass number. So if you want to find out the number of neutrons in carbon 614, you subtract 6 from 14, you end up with 8, and then you say the number of neutrons in carbon 614 is equal to 8. Right. So the last thing that I said, we would be focusing more of in units 4 and 5, that is the unit of radioactivity. So the SI unit of radioactivity is becquerel, denoted by the symbol BQ. This is in honor of Henry Becquerel, about whom we will be talking more of in video number 3. So 1 becquerel is defined as 1 disintegration per second. So there are other units of radioactivity other than becquerel. Number 1 here would be Curie, which is to honor Marie Curie. So 1 Curie refers to the activity of 1 gram of radium, and the other unit is Rutherford, of course to honor Ernest Rutherford, and 1 Rutherford is equal to 10 power 6 disintegrations per second. So the last slide that I thought I'd show you in this video is about the Fukushima disaster, which happened in 2011 in Japan. So the earthquake happened, and the Fukushima Daiichi plant had exploded. The 4 reactors, they caught fire. So of these 4 reactors, you'd recall reactor number 2 and reactor number 3 spewed, leaked out a lot of radioactive materials into the atmosphere and into the oceans. And the reason why I'm showing you this slide here is because of this. The SI unit of radioactivity is becquerel, and here you see 500 picobecquerels of iodine 131, 10 picobecquerels of cesium 137, and 10 picobecquerels of cesium 134. These were the amounts of radioactive leakage that were spewed into the atmosphere and into the oceans from this Fukushima Daiichi plant. So, right, I'll stop with this in this video, and I'll see you in video number 2.